the next speakers. So it's Trent Martin. Okay, I think that's good, Trent, and the floor is yours for 12 minutes. I will give you a warning after 10 minutes. Please go ahead.
Thank you very much. Besides myself this morning or this afternoon for you, I also have Dr. Robinson from the science pieces of this presentation. And these charts were also developed by Matt Atwell, who is in my office at Intuitive Machines, and Dr. Wagner from Arizona State University as well. So together we have combined on an effort to develop a hopper, which we're flying next year to the moon on our IM-2. The next chart, please. We believe that that hopper can actually be used for other missions on the moon. And in fact, what we had originally proposed using this hopper for was to fly down into lunar pits. And at this point, I will turn the presentation over to Dr. Robinson to go through some of Arizona State's ideas on how we could use the Intuitive Machines built hopper for these science experiments. Mark?
I think we have to remote walk first, right?
Yes, please.
Perfect, thank you.
Okay, so am I on now?
Yes, we can hear you.
Okay, pits were originally discovered by the Caguilla team. They found 3 of them in Mare deposits, and then we've subsequently found quite a bit more. And the reason they're interesting is twofold. One, from more practical sense, they could provide a benign environment for future lunar exploration and sheltering assets from radiation, micrometeorite bombardment, and thermal cycling. But they also have a potential to expose a record of Mare lava flow thicknesses and flow compositional variations over time. They also may preserve regolith between layers, flow features, and also in that regolith there may be a record of the solar wind. So, you know, there's a really fascinating and exciting science potential here. So the big question is, how extensive are these sublunarian passages? You know, they may be actually a speedlinker's paradise. They're relatively common, we now know. We've discovered 16 of them in the Mare, 5 in the Highlands, and over 250 in impact melt deposits. This little menu bar is covering up the bottom of my screen, so I think it's greater than 250. Let's see. Next slide, please. Okay, I guess Trent will talk about the hardware here. Well, all right, I'll just go ahead. And, you know, the key thing that we want to do with this mission is go to the Mare Tranquillitatis pit. It's one of the biggest, it's very well preserved, and it has the advantage that you can see the Earth from the floor. And we know that it has at least a, next slide please, at least a 20-meter overhang, and that we can see from off-nadir observations. The big question is here, what are the origin of these Mare pits? Are they skylights into lava tubes, which could result in a very large underground cave remaining? Next slide, please. Or are they collapsed pits, similar to many found on the Earth around basaltic shield volcanoes? Here's an example of Devil's Throat in Hawaii on the Big Island. Next slide, please. So I'll just quickly go over what our key science and exploration goals I mentioned before. We'll test hypotheses of Mare basalt in placement. Right now, the estimates range from a few meters up to 50 meters. Characterize relative timing of flows. In other words, were there long hiatuses between flows, or were they all deposited in very short periods of time? Determine the origin of the pit. Is it a lava pit collapse, or is it drainage into shallow magma chamber, or a lava tube? We'll measure the thermal environment inside the pit. In a sense, it's somewhat like an oven during the day because you get sunlight coming in from above and radiating off the walls. Okay, exploration goals determine the utility of the pit. What is the extent of the void and its roughness? Map out hazards for future larger landed elements, and test advanced pinpoint landing and hazard avoidance systems. Next slide. Okay, our measurement objectives, key science done with imaging, top to bottom stereo imaging the illuminated wall with 2 centimeter pixel scale, signal noise ratio of greater than 80. We'll measure the descent plume effects on the floor with 5 centimeter per pixel. And we'll image into the dark void to see what is there. From laser altimetry, we'll provide a wall profile centered in the image sequence, 10 centimeter spot, 10 centimeter separation. In an environment, as I mentioned, we'll measure the temperature of the illuminated area and the shadowed areas. Next slide. Okay, why this pit? Martin-Coltatus pit. It's got a diameter of 100 meters, a depth of 125 meters. We know that it has that sublunarian void already. This is illustrating what I mentioned earlier, that we can see under at least 20 meters, but we don't know whether it ends right there, where that vector from the camera is, or whether it extends forward. Okay, next slide. Okay, the daylight constraint. The Eclipse lander touches down when the incidence angle is about 45 degrees incidence angle. We need 50% of the pit floor illuminated at the start of hopper operations. And the mission duration is about 5 Earth days. That is when the sun goes from 45 degrees to minus 25 degrees incidence angle. And this is equivalent to land at a 9 a.m. to 2 p.m. mission. Okay, next slide, please. Okay, Trent, do you want to talk to the hardware?
Sure. So we're developing a hopper that we're flying next year. We can hold payloads of, in this case, 2 wide-angle 180-degree cameras, 2 medium-angle 39 to 51 degree, 1 narrow-angle 13 to 17-degree camera, 2 laser range alignment and medium-angle cameras, temperature sensors with a total mass of around 4 kilograms. We've actually been able to add additional sensors onto the mission that we're flying next year to the South Pole. So we actually have additional capability on the hopper. The hopper is an independent deployable spacecraft, comes off of a lander. In this case, our IM-2 mission, it comes off of the IM Nova C lander, but it could come off of, it weighs around 26 kilograms dry, at around 4 kilograms of payload capacity. It has about a 10 kilometer range one way, when fully fueled with 9 kilograms of propellant. And we have precision landing and hazard avoidance capability on the system that allows us to land within a 2-meter landing radius, which we will test with 5 hops on our first mission next year. And the hopper is around 72 centimeters tall and 76 centimeters wide. Next chart. So, as I mentioned, we will demonstrate this next year on a flight to the South Pole. Our intent there is to demonstrate
Yeah, Trent, we're losing you here. Maybe I'll just step in because we can't hear.
We have the camera systems on that hopper. We are adding pyrometer that to that hopper, and we are currently in the process of trying to add a neutron spectrometer as well to that hopper. So although the intent of that was prove out, can you guys hear me?
It's not very good. Sorry, the connection is kind of broken. If you don't mind, maybe Mark, could you take over? Because we heard you better, if you don't mind.
Yeah, okay. I think Trent just covered this exciting mission to the Czechoslovakia South Pole, so we'll just go to the next slide.
By the way, you're about 2 minutes left.
Yeah, okay. The basic ConOps are we land on the west side, we make a flight and take a little hop off just to test out the hopper. We fly over the pit and land on the other side to acquire a very high resolution map of the floor to help plan where we want to land. Flight through, we drop in, we're taking images as we descend. We only need to stay on the floor for, like an hour. Then we hop out, and as we hop out, we rotate the spacecraft so that we're imaging the north side instead of imaging the west side like we did when we landed. Land on the rim, transfer all the data to the lander. Then we can repeat flying, waiting till the sun changes and illuminates the other wall, and then repeat. If we get out and we have enough fuel, we can use that to fly over the Mare for a totally different investigation, collecting 2 centimeter scale stereo swath over representative Mare terrain. Okay, next slide, please. Okay, again, this just shows where the landing sites for the various hops. We go in twice. Next slide, please. Okay, again, just a little, we'll finish up on the slide right here. What we will measure the morphology of the walls and floor, the extent and topology of the void, the environment of the void, and what we'll learn from that, the thickness of Mare flows, floor roughness, origin of the pit, extent and roughness, environmental conditions. We'll test out key technologies, and there's important exploration returns. We'll determine the utility for habitat, and with science, Mare volcanism processes. Okay, I will stop there, and hopefully we have some questions.
Thank you. Thank you to both of you, and for being so brave, waking up so early in the morning, in Arizona. So we have some questions here. Do we have evidence of FTP lateral subsurface extent from subsurface radar measurements from Kaguya or others? And in that case, how far could you image the underground cave? What do you think?
I'm not aware of any definitive measurements of the extent of the sublunarian void, other than what we could see from, if you could flip back to that slide that shows the geometry of the imaging. Let's see, back. Right there. Oh,
yep.
Go the other way.
This one.
Okay, if you look in the upper right, on the right-hand side, there's 3 boulders in a row. I guess you can't see my cursor, obviously. But if you look on, and then the lower left, there's those 3 boulders right by the terminator line. Everything just to the right of those boulders is underground. So, and that measures about 20 to 25 meters. So we know there's an overhang of 20 to 25 meters. But that's consistent with a lava tube, but it's also consistent with the way these pit collapses happen on the Earth, where the opening is narrower than the bottom because of the way you collapse into these magma chambers. So right now it is not definitive. It can be either one. So that's the exciting thing about this, is we don't know how these formed, and we will solve that question by just simply landing in there and taking some pictures.
Of course. Maybe one more question here. How shallow would that magma chamber have to be, and is that a realistic scenario?
Well, these shallow magma chambers in these type of pits are very, very common on shield volcanoes on the Earth. So I think it's a very realistic scenario. In fact, I think it's, personally, I think it's more probable that it is a collapse into a magma chamber rather than, maybe magma chamber isn't the best word, into the plumbing system, right? And because they're just so common on the Earth. And they have, that very similar, there are no lava tubes, skylights of this size on the Earth. But, theory predicts on the moon it's possible.